So what I did was I put a breakpoint in Dolphin. Uh, do you know what registers are?
Uh, very roughly.
Okay,
Um, give me 1 sec.
sure.
Yeah, like there's like a fixed number of them,
Hmm.
and they have like names, and you can like load and like store
Yeah,
in them.
yeah. So most of the assembly operations will operate on the registers. Um, and whenever you want to do anything, usually you'll like load data from memory into a register, and then you'll operate on it on the like using the
Yeah,
registers.
and you kind of just have to like keep track of like what you've loaded into what register.
Yeah, basically. And there's also this is kind of an important detail. This is PowerPC. In PowerPC, there's I think I think R3 to R11 uh, are what's called volatile registers. It might be R12 actually. R3 to R12 are volatile registers, and then I think R14 to R31 are I forget what the non. I think it's just like non-volatile registers. What that means
Yeah.
is that whenever you do a branch and link, you can't. You're not allowed to change the values of the non-volatile registers. In other words, you have to
What
restore
what,
them.
what is a branch and link?
Okay.
Actually, and hold on just 1 sec. I'm gonna rejoin from a different device.
Okay.
Hello, can you hear me?
Yeah, yeah. I can actually hear you better now.
Um, okay.
Can you hear me?
I can hear you. I can hear you good.
Okay.
Uh, what is a what is okay? So what is a branch?
Okay. Yeah. So the good news is we have one right here. So a branch is pretty simple. You see how there's like this instruction here, or this like address.
Okay, so first of all, what are these columns mean? So the leftmost column is like,
The leftmost
and
column is the address where this instruction lives in memory.
okay, okay,
So you can see they go up by 4 every time. So that's
okay.
because
So
each instruction is 32 bits or 4 bytes.
yeah. So it's a little weird. Like in like the memory that you're reading and writing from is the same memory that your like actual code is in.
Correct. Yeah. They're in different blocks of memory, like sections, but this is like literally the raw memory addresses, effectively. Um,
Okay, and then what is the next column?
so
That's the instruction.
this is the instruction. In this case, B is a branch.
Okay, and there's just like some like vocabulary of or like language that specifies all the different like
Yeah. So
possible.
this is it's called PowerPC. Uh, and like there's different types of assembly languages or like interpreters. I don't know what.
Yeah, like x86 is like the main one.
Yeah. And this one is you can see microprocessor architecture that was developed joint whatever. It's an instruction set, right? So
Yeah,
yeah.
like
So
would could you make a faster emulator if you were running on a PowerPC?
I don't know. I assume they end up translating these or like emulating how they work. I can't say I understand exactly how Dolphin works internally fully, so it's hard for me to
Okay.
answer that question. There's like different parts of the GameCube that they have to emulate too, so like just that alone wouldn't be enough because the
Right,
GameCube
right.
also or the Wii also has like a ARM processor and stuff. But
Oh yeah. It's really crazy how how much they had to do to get
yeah.
it to work.
So
Yeah.
anyway, a branch is really simple. When this instruction runs, it just goes to the instruction that it's told to go to the
Okay.
address that it's told to go
So
to.
so hold on. So at memory location 801.6E740, you somehow
74C, right?
specified.
Yeah,
Oh, see, okay, yeah,
yeah,
the resolution's a bit off.
yeah.
Um, instruction, and and you have enough data to store what the next
So that's
What the
where
like
that's
argument?
that's a very good observation because like I said before, the addresses are 4 bytes, right? So you can't specify both that it's a branch and that a 4 byte address.
Unless you like actually use fewer bytes for the address.
Right. So that's the trick. It actually uses an offset. So it's an offset, and that's all handled when you like run this through an assembler or whatever. Like normally you just like tag it with a label, and then when you branch to a label, it'll calculate the offset from the instruction that it ends up at to the instruction you want to go to.
Right.
So because
Right.
it's an offset, it's a much smaller size. So there's I don't know how many bytes are available to it. It might be 2, it might be 3. I'm not really sure. Um, but it's enough that I can do that. We could probably find that. Let's see. I think coding PowerPC ASM. I think this is what I want. Nope. It used to be what I want.
Nope.
Damn it, that was a good website. That had like a whole bunch of like a really simplified list of all the instructions. Oh no. I hope I saved it or something. Ugh. There's sites that like break down the structure of the. Oh my god, I don't want a PDF. I really don't want a PDF. I think the IBM site has. Oh my god, this is terrible. Okay, I give up. I can't find how the instruction's built. But basically, it's an offset. That's how it stores enough data to go to a certain location. So anyway, so that's a branch, right? So the question was what a branch and link is. A branch and link is very similar, except that it'll store the instruction it came from into a special register called a link register. That's what you see here as LR.
Wait, okay. So there's a special register called LR,
Correct. And that's the link register.
which looks like it's number 18.
No, no, sorry. These are completely different. So this is the value of R2, and this is the value of F2.
What are Fs?
Floats for float
Oh,
arithmetic. Yeah,
they're just float registers.
yeah, they're
Gotcha.
float
Okay.
registers. Yeah, I almost never have to deal with the float registers. So you only really need that if you're doing like, I mean, float math, obviously, which is not that common. Um, but yeah, so there's this link register, which is a special register. There's also other special registers, like this is I think program counter is what PC stands for. That's our current instruction location.
It's
Um,
like dangerous to mess with that one.
yeah, you can if you want to jump around the code randomly without the thing controlling. A lot of these are dangerous to mess with. I wouldn't. If you start changing some stuff, your game will crash. But um, then there's like CTR and CR. I think these are compare registers. Like when you do a compare operation and you want to like do a conditional branch, it uses these. Um,
Okay.
I don't know what the other ones do. Yeah. All right. So yeah. So branch and link, what it does is it does a branch, but it also stores something into the link register, which is the instruction it came from. Then I was talking about stack frames before. Stack frames are effectively so you have also a stack pointer somewhere. I think stack pointer is an R1. So R1 is also kind of a special register, and it points to your stack, which is a location in memory that you can kind of just use, that you know is safe, because it's managed by every function call. So when you do a branch and link, what you have to do is you have to back up your link register to the stack, and then you can like do other stuff, call other functions, and by the time you return your function, you have to restore everything you stored to the stack back to the registers. So that includes all of the what I was saying before, the non-volatile registers. You want to store them all back into their non-volatile states because the person who called that function expects them to not change when it calls a function. If that makes sense.
Yeah, that makes sense. That
Yeah,
makes sense.
because like you can
Okay.
see it in this function. You call a BL, And then if I had a variable loaded into R14 needs to be the same value here. Otherwise, shit would break because it expects it to be the same, right?
Right.
But
Right.
R3 doesn't have to be. In fact, it probably won't be. All the volatile registers aren't expected to be the same
Okay,
when
but
functioning.
okay, so that's basically what non-volatile means.
Yeah,
Yeah. Okay.
yeah.
Gotcha.
And
So the
also,
size of a stack frame is equal to the number of non-volatile, or like plus a few.
that's what we do. We just back them all up, um, because we're lazy and we don't want to write exactly what we do. But when you have a compiler, it'll only add the specific ones it needs to the stack frame so that it doesn't have to back them all up all the time.
Oh, I see, I see. It'll sort of like figure out which ones
Are
you
used.
don't touch.
Yeah, exactly. Yeah, exactly.
Careful, because it's like all the ones that you're like caller, the thing you're calling can call other things, and like
Yeah,
transitive.
but if you call other things, that function is then responsible with restoring it, right?
Oh yeah, yeah, that's
So
right.
like that's why it's kind of nice. You only have to worry about your own scope because if you call another function, that function will always, store and restore everything. Anyway, the point with the link register is you store it to your stack and then you restore it at the end because if you call another function, it'll override the value, right? That's why you have to store it. And then you load it back into the link register at the end, and then you can do what's called a branch link return. So what that branch link return means you're returning to the position of the link register. So that's the end of your function effectively, where you're returning to the caller. Did that kind of make sense?
Yeah, okay. I'm still not sure like when you'd want to just branch and link, and then just or branch link.
Correct. Yeah, I think if you're calling a function, generally you always branch and link because you expect the call to come back to and like it continues sequentially.
Right, right.
But if you
But
want to do
it's
like
like an if statement, you might
right,
want
an if
like
statement is a
branch.
branch, uh, or like a switch statement or whatever.
Right.
Yeah. Um, that said, all right. I think that was a good summary. But
Well, yeah, I think I got a much better handle on this
yeah,
one.
yeah, you seem to get it. Um, anyway, all that said, we when you're operating with pure Gecko codes, all you can do is branch instructions. So the way Gecko
What
codes
what
work,
what what is Gecko, by the way? Like I keep hearing the word, like
yeah,
it's some sort of operating
it's
system.
a lizard, obviously. God, I can't find anything I want to find. Thank you. This is what I wanted. There's a code type documentation here. Okay, what Gecko is, I don't know if I know the exact history, but I think it was built into the initial, like, by Nintendo to some degree to allow for some debugging. And there's effectively a code handler that's injected into the game, but like at the very start, and it sort of runs like every frame, and it processes some codes, and those codes do specific things. So the codes are in a specific location in memory that is like not used by the game, and then every
Yeah.
frame those codes are iterated through, processed, and then applied. And what those codes do, usually the ones we end up using are 04 is one of the ones we end up using. The way 04 works is it will override the data at this address with what you provide here. Uh, did that make
Right.
sense?
Yeah, yeah.
Okay.
So that's like okay. That's like the simplest one.
Yeah.
And these Gecko, this is like the like NetPlay community settings cheat.
Right. Yeah, you'll see it actually if you look at like let's see. If I look at
Just
one of
but
these out like these gale01.ini or whatever, right?
yeah, yeah, yeah.
See this is
They
a
have a bunch of
04 code, right? And
okay.
so it'll override it's actually you always have 80 in front of this address. So it'll override whatever is at 8045BF28
Yeah,
with Fs. And I think I don't know exactly why it does that, but sometimes you're overriding instructions too with these 04 codes. Sometimes you're overriding memory, sometimes you're overriding instructions.
Yep.
Like this is an instruction, I think. I don't know, it might be a branch and link or something.
This runs every frame.
I believe it runs every frame, yeah.
Okay, so does like Gecko run like outside the game? Like, does Gecko have its own notion of frames?
So I
Or is that like beyond the
I
scope of?
don't know exactly how it works on console. Uh, I think it might be something like Nintendo deals with it. The way it works on Dolphin is that there's like some hook or something where Dolphin will literally take the program counter, which is that register we were talking about, and put it into the Gecko code handler, and then put it back when it's done. So it'll literally like manually modify the program counter so that that code runs.
I see. Because is Gecko, are all these things like just valid um like operations that you could just execute like a normal program,
Right.
or
Well,
does it have it has its own
so the code
language?
handler is what Dolphin is gonna do is it's gonna change the program counter to go to the code handler, and the code handler deals with loading all of these and then doing like we talked about a zero when it sees a 04, it's gonna replace this address with this.
The code handler is itself written is like a PowerPC
Correct. Yes.
program.
Yeah. That's injected into the game like it's injected like into a location in memory where the game doesn't touch.
I see. Oh, I see. And Dolphin manually changes the program counter around
Yes, in order to
through
call it.
some logic, and then console does it some other way.
Yeah, I
God
assume
knows.
if you're running like Nintendo, the Nintendo does it. Uh, I have no idea what happens if you use like the memory card exploit and you add the Gecko. Yeah, I don't know exactly how. But
Okay, because I'm asking because it seems relevant. Because like if we do a speed hack and some of the game's running faster, how do we know that like that isn't
mhm.
played badly with Gecko?
Well, the good news with this code handler, so Gecko was originally built, I think, so that you could use like the Gecko USB and you could like provide these codes while the game is running to change stuff. We don't really use it for that. We just have like our default code set and it doesn't change. So if you have 04 codes and C2 codes, even though it keeps applying them every frame, it doesn't matter because they're not changing, right?
I see.
So
Okay.
even if it wasn't running more, it wouldn't really matter.
No, I was sort of worried about the opposite. If the game's running too fast, then
hmm
it's like misses the Gecko code handler like
hmm Yeah, yeah, yeah.
frame, depending on how that hook is set up. But anyway, maybe that's just not a problem, and we don't have to
Yeah,
worry
I
about
don't. I think that's fine. Uh, but anyway, so
it.
yeah, so 04 simple replace, and then there's also 06 that we use, which is over here, uh, but it's not used very much. It's kind of like it's very similar to the replace, but it's like a block replace, um, where you basically specify a bunch of data and you like the start address and then how long your data is, and then you like
Okay.
replace a block of code or of data.
So,
Um, but the one that we probably use the most, which is like the one that's kind of the most powerful one, is C2, and that's down here. Where is it? Did I miss it? Here we go. It's insert
oh, wow.
ASM. So what it does is it converts the instruction at the address you specify to branch to this code block you're creating. So you create this code block, and then this will branch to your code block at this address. This is the size of your code block. So
Uh-huh.
so we can kind of like look at one of those. So you have a C2 code here,
Yeah.
and then this is the address where the branch is going to happen, right? So in fact, we can go look at that right now. So this code is currently applied, I believe, in my current running instance. So we can go look at it. So,
This is live.
well, see how this has a branch here?
Yeah.
Normally it doesn't have a branch there. That was Gecko that added that because we're
So it just overwrote whatever the hell was there.
correct with a branch.
When you're applying when you're like doing these cheats, you have to like try to find a good place to like
Correct. Yeah.
overwrite. Although I guess you can always like overwrite something and then at the end of your code block do the thing that it was supposed to do anyways.
Correct. That's what we do. Yeah. Sometimes it makes sense to do it at the start of your code block, though. Also, it kind of depends what the instruction is, where you're injecting.
Yeah.
You also have to be careful because you know how we were talking about non-volatile registers and volatile registers.
Yeah.
If it expects a certain value in a volatile register, like because you're adding a branch, but it didn't expect a branch there initially, so it might afterwards expect something in a volatile register. So sometimes you might have to like back up your volatile registers too.
Right. Right.
Only
Right.
because you're interfering with the way the code was compiled, you know?
Yeah. Okay, that's really cool.
Yeah.
Did you know there's a guy who somehow he was working on like compiling C into like using a PowerPC compiler into Melee to like
hmm
do
I've heard
mods.
people have done that actually. I don't know too much about it, but I've heard that's been done.
Yeah.
I don't know how well it works or whatever, but it's pretty cool. Uh,
Um.
okay, so anyway, now what? Now this is a block of code, and that code is compiled via the software we're going to use, and it looks something like this, for example, like what we were looking at, right?
What does compiled mean? Why do we
So,
need to compile it?
sorry, not compiled. I think the real term is assembled. I always say compiled, but I mean assembled because right now it's text and we need to convert it to bytes.
Okay. Wait. Hold on. So you wrote this .asm file, and are you just saying that this gets turned into like the bytes that we were seeing before?
Correct. Yeah. In fact, we can look at this one. This is the exi transfer buffer.asm file. So if we look
Okay.
at the playback code, let's see, where's the output? Playback, what we were looking at before. Here it is.
Okay. So
So it
that's
gets
just
turned
like
into this. This is the same as uh, this.
okay. And there. Oh, I see. I see.
It's like the byte representation because like these when we write these instructions, they can be translated to just be bytes, right? Like all of these instructions are 32-bit operations.
Right. Right. Right.
And so what
So
the
how,
assembler,
how how complicated is this? Is this like translation?
I mean, I think it's
Like
pretty
just
simple,
macros,
right? Because
or
it's
does
like
it do other stuff like because you were saying like when you jump to a label, it like computes some like offset.
right, yeah. So that it is smart in that sense. And also you can like define variables and then it'll like replace those in the assembly and stuff. This is so like it's more readable when
Right.
you're
Right.
like writing. So it has like helper things that make it. But it in general like this is a move register operation and it can get translated to like a 32-bit uh, instruction.
Yeah. Yeah.
And so that's what the assembly process does.
Well, yeah.
And then that's how it ends up being. Uh, God, I keep losing my place. Yeah, that's how it ends up being these things. Okay. Um, so back to what I was saying before. So this is an exi transfer buffer function. We want to be able to call it as a static function because we want to call it from a whole bunch of different codes. Unfortunately, our codes are like it's easier if our codes are all in different files because they're all at different injections. And so we can't just use a label across files and have it know where those are going to end up being in memory because this isn't just our program. We're like injecting into some other program where we don't really know where the memory is going to be.
hold on. What does inject mean? Inject means that like I thought. So this is like the C2 code
Yeah,
in Gecko.
yeah.
So like this. So all of this like assembly thing that's gets turned into bytecode, um, in like the Gecko memory location. Is that right?
It gets so the exact code that you just saw here gets copied to some memory location. It gets processed by the code handler, and then what the code handler does is it reads that this is a C2, sticks a branch where you said you wanted the branch, calculates where it's going to put the act or like it knows where
I
it
see.
knows where this code exists because it's like right where the code is, and so it branches to that. And then the C2 code is also smart in that it'll also branch back at the end. It'll add its own branch at the end to branch back where it came from. So it's kind of like
The Gecko code handler decides where this like chunk
yes,
to will go, but like that it's in some undetermined memory location.
correct, yeah. And
I assume I guess in principle could be like different each time you go there, but that's
yeah, I think in
unlikely.
practice it'll be the same because the place where gecko codes are stored is fixed. As long as like you have your gecko codes all in the same order, because they just get like grabbed and slapped into memory.
Yeah.
But if you change the order, then yeah, they won't be in the same place.
So in principle, you could just look at your Gecko code list and then pre-compute where all these are, but maybe that's like too risky. Uh,
Yeah, you could potentially pre-compute where they are, yeah, and then you could try to branch to them manually. Uh, but that would be annoying to manage.
yeah, because what I'm hearing is that you want to define like one function and like branch to it from
Correct.
like
And we use kind of yeah, that's correct. So what we do is we inject it with the normal C2 bytecode into this location. This location is like kind of static memory that there's nothing happening there, so it's a safe location to just inject into. So what that does is it converts this address to a branch. We can go look at this address, and you're gonna see it's a branch. Okay, so this is a
okay.
branch, and now this is branching to our code.
Oh, this is like a this is the thing you're calling a prefunc.
I don't know. I
No, was that tau? That might have been tauken. I was talking
It
about
might have been. I don't really know what he means by prefunk. Uh,
it's a function that like calls another function.
right. I mean that's kind of what we're doing. So we're gonna like this is calling a branch, which then calls our code, but then our code is effectively written as something you're technically supposed to branch and link to. So it ends with a BLR. So we're gonna branch and link to here, which will write the link register because we branch and linked, and then but that will branch to the actual location where this function's stored. And then by the time we do this branch link return, it'll return to where it got called from.
Okay,
Because
the intermediate like branch is a plain branch. It doesn't ruin the like BLR logic.
right. Yeah. A standard branch doesn't do anything to registers.
Right, right, right.
So it just kind of like forwards you to the right function. Normally, you'd just go to the right function right away with your branch and link. But since we're using C2 codes, we have this like intermediate step.
Right, right. Okay, so you have like so somewhere in static memory you have like a global like dictionary of like various functions.
Exactly. Yeah, we store that in this common.s file. You can see here, this is where we define the addresses of our static functions.
Cool. Yeah, this is really fun stuff. I love how you're like yeah building up a
Yeah.
library.
Yeah, it's definitely really cool to mess with. Like when you start messing with Melee and then you like stuff works, you feel like all powerful. But yeah, so anyway, so we have these now, and if you look in the code for places where like this is referenced, you'll see This is actually a macro. Uh, the reason it's a macro is because this is defined as a full 32-bit address. And so, as we discussed before, branches are actually offsets. But there's actually some other smart ways to branch, which is if we go
Oh, right, right. You can't branch to a full static.
exactly. That's something. Yeah, you actually called that out right away that you can't do. It doesn't make sense. You don't have enough data to do
No.
that. So the workaround is there's other ways to branch, and I'll show you what. So this is our macro for branch L, which is what we were looking at. And macros are kind of weird. These are two args. So this arg is the register, which was R12.
Right.
So we're just using a random volatile register, the last one. We used the last one, I think. Uncle Punch wrote this macro, not me, but I think he uses R12 usually because it's least used by the game. I think the compiler, when it compiled Melee's code, tends to use the lower registers first and only use R12 if it needs it, which I think is like almost never.
Oh, like Nintendo's like PowerPC compiler.
Right, yeah. So anyway, so he used R12. So we call this with branch L R12, and then this is a full 32-bit address, right?
Okay, and this expands to like 4 lines.
It expands to 4 lines, yeah. And what it does is this is a load instruction shift, or sorry, load immediate shift. So what load immediate shift does is into our register, which was R12, it grabs the high 16 bits of the address we passed in. It loads it into this register and shifts it to the left. So after this, the value of R12 would be like 0x. I forget where I was when I was showing here. Let's just use so let's say we're calling it with this, right?
Yeah.
So after we call that function, our value that'll be R12.
Yeah, I see.
Because we loaded the high 32 bits and we shifted them to the left into R12. Then we do an OR immediate with the low bits. So after that, it'll be the full thing.
Okay.
Does that make
Wait,
sense? So the OR immediate,
the resolution's a little low, but there's like, so it's like slash or like backslash address, and then what's that? Is that at? What
this
is
is
the
at L. At L
at L,
means
and then what's the other one?
yeah, at L means uh, the low bytes of address.
Okay. Oh, the other one. Okay, at H is like high bytes.
Yeah,
Okay,
correct.
gotcha.
Yeah, and that's like a special macro thing you can do.
Okay,
But yeah,
you
so
can
this
just
is it's an OR immediate into R12 with R12 with this value.
yeah. Got. Why the hell do they do that? Or like why not just write or 12?
Why is it R12 twice?
Like you're ultimately you're now R12 will hold the value address, right?
Yeah, yeah.
Do that directly. Like I'm confused why you need to like write it in.
In two operations.
Yeah, first the high
It's the
bits, then the
same
low bits.
issue as before. We can't fit a full address into and an instruction in 4 bytes.
But all you need is an instruction, a register, and a value.
Right, but that value is 4 bytes, which is all you have.
Wait, I thought you have four. Okay. At 8 byte, like 4 bytes, and then another because it's like usually 2 columns.
No, you have 4 bytes total.
But each. Okay.
So, so this is 1 byte, right? This is a second byte. And
Yeah. So that's okay. For some reason, I just thought that like assembly code always like it comes in and like each line has like if you go back to like the gecko codes,
like this.
yeah,
Yeah.
it's always like 2 columns.
Yeah, I don't. I think they just do that because it's like easier reading because like this code goes together. But this is 4 bytes and then this is 4 bytes. But every instruction is 4 bytes total.
Okay.
So like these are all 4 bytes. You can see by the offset. Like MFLR R0 is defined in 4 bytes. Store word R0 with like this offset and register is also defined in 4 bytes. So everything's 4 bytes.
Okay. Okay. I sort of sorry. Yeah, I was sort of thinking about it as like they come in pairs where the first one is like second one is like the argument, but that's like not actually true.
Yeah, no, it's just all together in 4 bytes. So it includes like the instruction code as well as all the data required for like making this possible.
Okay. So like write like copy R18 would be like 1 4 byte. It contains like both the write instruction and R12 and R14.
Which line were you talking about?
Oh, no, I'm just coming up with a hypothetical line. Like if I wanted to like copy R12 into R13,
Yeah,
presumably that's something you can do.
it's move register.
Then
That's MR. Yeah,
okay, and then so it'd be MR R12 R13.
yeah, that'll
Uh,
move the value of R14 into R12.
uh, okay, and like thing gets turned into 1 4 byte
Correct. Yeah,
instruction.
that whole thing is 1 4 byte. God, I really wish.
Okay, gotcha. Okay, so in this macro, address is literally just like
Jesus Christ.
address is like a hard coded value.
Uh,
Okay, so then the at L and the at H is just like
yeah, you
okay,
can see
yeah.
how we. Where was I?
That's like the at L and at H is done like at like assembly time. It's like pre-computed.
Yeah, it like just like kind of figures it out. Cause see, this is like a kind of a constant, if you will.
Yeah, exactly, exactly. So
Yeah,
the compiler literally like
yeah,
bits and then like writes like yeah.
yeah. That's right.
Cool, cool. Okay. I'm
Cool.
up to speed.
Yeah. So what we're doing, we're loading this entire address into R12 using 2 instructions. Once we have loaded it into R12, we're doing this stupid instruction, which is like move to CTR. CTR was one of our special registers, and reg is still R12. So this is like we're moving the value of R12 into the CTR register, and then we're using this special instruction, which is branch CTR link. So it branches to the address in CTR and links.
Okay.
So every time we have this branch L function, this branch L macro, it's actually 4 instructions where it'll load this address into the register that we chose, and then it'll move the value of that register into the CTR register, and then it'll branch to the value that's in the CTR register. You can't say like, I want to branch to R12. That's not possible. That's why we're moving it to the CTR register.
I see. I see. Gotcha. Why even use R12?
Uh,
Write directly to CTR? Like write the high bits to CTR,
you
write the low
can't do
bits to
that.
CTR. You can
You can't do like load R. This doesn't work. You're not allowed to interact with the CTR register that way.
okay. You
That's
can
why we
only
have to
move.
use our volatile registers and then use the move operation. But yeah, if we could do that, then yeah, we could do that. That would save 1 instruction.
Yep. Cool.
All right. Um, cool. So anyway, that's basically I don't remember where we were before that, but
Yeah, we got to link back to the
yeah,
pop the stack.
yeah. So um, I feel like at this point I should just like continue with uh, what we were doing, and you can ask questions
Yeah, I think we're
because I think it sounds like you have a
fra-
decent base now.
um XC transfer buffer.
What about it?
Okay. No, I was just trying to remember where we were. Okay.
Yeah. So what I was gonna do, so I guess what I was saying is I was gonna maybe go back to trying to add in those hooks in those specific locations, and then compiling that code and then running that code on console. Or actually, first I'll run it on Dolphin just to see, um,
Okay.
and because
Okay.
that'll be what you want to do anyway.
Yeah. So okay, so you're adding a.
Yeah. So
Okay, maybe you can just explain again what you're trying to do because I think it'll make a lot more sense now.
yeah. So what I'm trying to do now is so I grab this common.s thing, this header, and I grab the exi transfer buffer file. And what I'm going to do is I'm going to add hooks in specific locations in the code. So in other words, I'll add one at the start of this start melee function that I was telling you about. What's going on here? Oh, so I'm going to add one at the start of the start melee function, and which is going to add a C2 code, which is going to be an inject code. It's going to inject my code, and what I'm going to do is I'm going to call the exi transfer buffer function that we've written in a static memory in order to like access the DMA function, the DMA thing in Dolphin, because that's effectively what's going to end up happening. Is it's going to trigger the exi DMA, and then Dolphin is going to process that. And I'm going to write a logger because I want to see the time intervals in between different code locations.
Yes.
Does that make sense? And I think for you it'll be very similar. You'll write your injection somewhere, you'll call the EXI transfer buffer, and then that's like your location. That's your hook effectively, where you can like read all the memory locations you need.
Yep.
All right. So let's try to just add one at start melee real quick. We'll just do one for now. So I think once I do this, you'll have basically what you need. And we can help you find like a good place in memory to put it, because like we mentioned before, you have to be a little bit careful because you don't want to put it somewhere where it's relying on like those non-volatile or those volatile registers to be certain values.
Yeah. I think Taukan was mentioning that I should do it right before Dolphin starts pulling. What I do is I'm gonna once I one in the Dolphin function, the read or whatever DMA, then time for my AI to like read the game state, compute an action, send it through the pipe input, so that the game can keep going, and then all the like inputs will be there when it pulls them.
Yeah. I mean, if Talcon has like an idea of where to put it, that's probably good. I don't know exactly where the best place to put it would be. But anyway, for mine, I'm gonna put it in start melee somewhere, right? So this is start melee. Here this is it building the stack frame. Notice how it only writes R31 and R30 to the stack frame. That's because it knows those are the only ones it modifies.
Okay, cool. And because like people didn't write this. This was compiled.
Correct. Yeah. This is like real code in Melee. And you can see the SP is the stack pointer, which is it's an alias for R1. So what's annoying is like this. I'd like to do it. I'd like to do it before this, So maybe I would actually follow this branch. Perfect, I think. Oh, this doesn't even really build a stack frame. I guess it doesn't call any functions. Oh no, it does call a function. Where is it? How does this work? It's not.
You're asking me.
Oh, here we go. Here we go. Okay. This is really bizarre. So this is where it stores R0. So you'll see them start with like move from link register. So this is move from link register R0. This is often how the stack frames start. It moves the value of the link register into R0, and then it does like a store word for R0 into like this memory location. So this is the offset, and then this is the register which contains the address. So the stack pointer contains an address of the stack pointer, and then this thing writes R0 at the stack pointer location plus 4.
Right. That's because that's how stacks work.
Yeah. So I think, but what I find really weird is that this thing like does this like load is R3 here before it writes the stack frame. So this is just like a really weird function. I don't know why the compiler did this. But anyway, what I'm gonna do then is I'm gonna do it here. So this is the address I want to inject at. So I'm gonna do. I did copy address and then I grabbed that address. Why does that thing keep showing up? I don't know what. Okay. So I copy this address. So now the C2 code is going to get created and a branch is going to be added at this address to branch into whatever code I put in here, right? And then my code is effectively just going to be I don't need any of this. I don't need this. I do need this, so I'm gonna do a backup. I'm gonna do a back. So this is yes.
I love how you just deleted everything so that
yeah.
I don't have to understand it.
Yeah. So this is like the effectively the structure of our code. It's great. Oh, I don't even need this. Beautiful. So it's going to do a backup and then it's going to do a restore. And in between that, what I'm going to do is I'm going to do a branch L with this guy. So R12 here. But I also need to load the args. So the args for our transfer buffer was like a pointer to our buffer, which we're not going to use anyway because we're not going to write anything to it. And then the buffer length, which we'll just do 0. So we'll just do like load immediate R3. Actually, we're going to do this. You move register R3 stack pointer. We'll just put the address of the stack pointer in there. It doesn't really matter anyway. And then load immediate R4 0. We'll just put R0 as the length, and then load immediate R5. We'll do a read. Right? Does that make sense?
Okay. I'm blanking a little bit. We're storing a bunch of stuff in R3, R4, and R5. And we're doing that because that's sort of the convention for...
That's how args are passed to functions.
Okay.
Yeah.
So, functions typically, they'll start at R3.
R3 will be the first arg of a function, yeah.
Gotcha.
And then also outputs are returned the same way. So you might have an output in R3 if the function has an output.
I see.
Because they're volatile registers, right? So it's legal for them to change. And that's actually used to its advantage in this case because it's used to like return a result.
Gotcha.
Yeah. So these are our args for this function. So we're just going to call it. And then now we have to do one more thing, which is we have to not break the existing code because we're replacing this line, right? But also, what I was talking about before, this one is gonna be a little bit weird because this line was weird. So I'm gonna rerun this line too, because it probably expects R3 to be like something somewhere. In fact, it expects R3 to be this value for this call. See what I mean?
Yeah. Yeah.
So I need to reload R3 because I changed R3. So I'm gonna do both this. I'm gonna do load is R3 and then this value 0x804a. Let's see if I remember that.
Oh man, this is like a little scary.
Yeah. I don't think it matters if I do it before the restore or after the restore. I'll do it before because that's. Oops. Okay, so we'll do like a load is. Was it R3 0x804a? Was that it?
I think so. But
Yeah. Load is R3 0x. Can I? I don't think I can copy like. Oh, maybe I can. Does this work? Hey! That's much easier. Okay.
is that was that the right line?
Yeah. It's this thing. Sub I R7. This is the one we're replacing.
Oh, I see. Oh, okay. Gotcha.
So now we should be good. I still, yeah, the way this thing generates its stack pointer is very confusing to me. So because of that, I don't know if this is going to break, but I don't think it should break. It should be fine.
More stack pointer stuff. So all these like STW is like store or something?
Yeah, actually, I don't like the fact that it does another stack pointer thing here. I shouldn't interrupt like it writing the stack frame, because then I'm going to be using its previous stack. Yeah, that's going to break for sure. You want to do it after the stack frame's written, so we're going to do it here instead. And this,
You have to know like which line it is.
yeah. Well, I have the address of the line I'm replacing up here anyway, so I'm going to replace that line. And then I'm going to do copy code line. Now, what I don't know is if I also need these two. I think I do, because they're probably used, like, where is R3 used? Next. It's overwritten. Oh. Okay, I'm just gonna do it.
Why not do it right before all that stack pointer stuff?
It kind of breaks the flow. I think maybe we could, but I think usually we don't inject there. Because I think the start of a function is defined by like this MFLR usually. And if I like do it here, then it's like actually I think the link register restore will be wrong, so that the branch later on will be wrong if I do that. Because this has to move the value of the link register, which just got set, to R0, and it needs to be right. And then it needs to be able to back it up, so that when it goes and branches later, it branches back to the right place. Did that make sense?
Yeah.
So that's why I'm doing it here, because I want to do it after it's written its stack, so that its stack is correct.
Right.
So I'm gonna do it here, but I'm still gonna execute these two lines, because I don't know. That's the value they would be.
I guess
if I didn't mess with it. So
you could either spend more time trying to like figure out what it's doing, or you could just do that. That should just work.
This should be safe, because this should put it back exactly in this state. that it was. Just make sure. And these are backup and restore, by the way. So
Oh, okay. Yeah, right. The macros. Yep.
yeah. Oh, I forgot. I use R0, so I actually want to do. I want to do this after.
That there's just like pitfalls all over the place.
It's risky. I think I'm also not like super experienced. I'm like decent. I can work my way around, but people like Uncle Punch and Tokan are much more experienced with this stuff than I am. Um, okay, so I think we should be good. So now let's build our code. So I built a tool which helps you build multiple files at the same time. Previously, what people like Uncle Punch would do is they would compile all of their codes manually, like individually, and then write the output into some file, and then like manage that file manually, and that was a shit show. So
Jesus.
yeah, so I wrote this tool which makes it a lot easier. And I'm gonna grab this one. Oh wait, no, I want this one. So it uses a configuration file to sort of explain how you want your code to build. So I'm going to grab an existing one, and you'll see the output path is specified as to be like output netplay gale1r2.ini. That's what I was browsing to before. Like if you look at the Slippy SSBM ASM
Yeah.
repo, it has this output directory, then it has netplay, and then this is the output file. So that's how it specifies the output file. And then you specify all the codes that you want. So like the first one is faster melee netplay settings. These are all binary codes because they're not written by me, so I just like added binary file so it loads those. This one's binary. So I'm gonna leave all of these so I still have these in the file. Widescreen, this is fine. External. Oh yeah. I guess the widescreen wasn't an external. I don't want the widescreen. I'm going to delete it. Okay. I'm making sure because I took this from somewhere else. I'm making sure I'm not referencing files that I don't have in this location. Okay. So Slippy recording we don't need. We're going to do like test inject, right? And I'm here. You can be one of the authors.
My first, first publication.
Yeah. Okay. And then this is like the different kind of subcodes that are part of this code. So we only need one. Okay.
And these JSON, this is like your like syntax for specifying.
Yeah, this is my program will read this JSON file, and that's how it figures out how to like which files to assemble, and then like how to build your output the way you want it built. So we're actually gonna look at the playback one.
I have to go to bed pretty soon.
Yeah, I feel you. I think we'll at least be done with this really soon. So, okay, so this is inject folder. So what this does, Yeah, I think once like this will be done pretty soon, like within probably the next 10 minutes. And then after that, you should probably have a good base. Hopefully you feel like you learned something.
But yeah, I've already learned a huge amount. This has been super fun.
Yeah. Um, so I'm gonna move
Okay,
my.
thanks for
Yeah, no worries. It's fun. I like talking about this stuff too. So plus I'll probably keep this video. I'll probably save it somewhere in case anyone else wants to learn, so I can link them this. Be a useful place to start, maybe. Okay. So I put my stuff in this codes thing. So source folder is codes. So it's gonna basically build everything in this folder, which is really just two files. The header file gets ignored, and then that's gonna make our code. All right, let's just try it. I might have messed up somewhere, but we'll know soon enough. Where am I? Here. Okay. So let's see if this works. Oh. Gecko build -h. This is my tool, but I didn't remember what the what the arg was. Jeez. Failed to write file. The system cannot find the path specified. Okay, yeah. So I forgot to make this. We'll just do. Hey, okay. We built a file. Let's see if it looks right. So this has all like the base stuff. This is like the net play codes. These are like the other stuff. This is our test injection. So here's EXI transfer buffer, and then here's our code. So we did it, maybe. You ready to see if it works?
Yeah, cool. I don't remember what it does.
It just writes the DMA. It does a DMA read. That's all it
Oh
does.
shit, I think I missed the part where we actually wrote the DMA read.
Yeah, that was this.
Oh, okay.
Yeah.
DMI. Oh, okay. Wait, it does a transfer buffer.
That's what this function does. Is it does a DMA read or DMA write based on
Okay. That's like it's a big function.
fairly big. Yeah.
It's like the big one that's before our small one.
Correct. Yeah. Yeah.
Just
Our
okay.
small one is it's not too big. It's like this.
The big one just like sets up like I am a library function at this static location, and then the small one just is
The small one calls it. Yeah. All right. So I'm going to copy this over to my Dolphin instance now. Sys game settings. I'm also going to kill my Dolphin instance. Just going to restart the whole thing. You don't have to restart it, but I'm just doing it because I was sick of that stupid window that was open behind everything. Okay, cool. So I added my new codes, right? And then I'm going to open Dolphin, and we're going to go look at what codes we have available. So you'll see, here's our code. Test inject, written by Fizzi and xpilot. All right. And then we're going to hit play. All right. Now let's go make sure our injection is where we expect it to be, right? So we can...
Oh, okay, you're gonna use the debugger to like.
Yeah, we're going to make sure... Okay, cool. So we have a branch. Remember we were looking at this function before with the weird load and then the sub I?
Oh, yeah. And
Yeah.
then we decided to put it after those
Yeah,
SPs.
exactly. So now we have a branch where we said we wanted it to be. And if you follow this branch, this is our code. So this is us loading those args.
Huh.
And then this is...
This is with a backup and restore, like...
Yeah, backup and restore, that's here. That's these 4 lines. That's the backup. And then this is us loading our args. And then this is our macro here. You see it's like, you see how it's converted to load is R12.
The branch L?
What's that?
That's the branch L macro.
Yeah, yeah. Remember we were looking at it. It did like
Uh,
the register you asked for, and then the top half, the high half of your register or of your arg, and then the low half of your arg. Yep. And then this is restore here, right? And then these are our replace code lines. This is a no op. Sometimes it just adds one in for no reason. And then this is our branch back, which will go to this line, which is the next line. Does that all make sense? I don't know if I can't hear you or if you're not saying anything.
oh yeah, it does make sense.
Okay,
Yeah.
okay. Sweet. Um, okay. Now we'll just use the dummy. Oh, also I think this is currently configured to use port B. I think that's where is that configured? Oh, it's configured here. You can change this constant to 0 to do slot A or 1 to do slot B. So yeah, so this will use slot B. So I'm going to put the dummy in there. Why does it keep doing that? This is really frustrating. Is there no... Okay, whatever. Put the dummy in slot B. I'm going to make sure my logging is set up to be correct. Expansion interface. So that's where the dummy logs, and then it does an info log, so we have the right verbosity. So it'll work if...
Oh yeah.
You can see it gets some stuff at the start of the game. I don't know why, but now I'm gonna plug my controller in.
Okay. So we should only see stuff on start melee, right?
Correct. So when I actually start the game.
But the game is started.
Sorry, when I start like a game, like
Oh, start melee. It's not like it's not booting like.
Yeah. Sorry, it's when you start a fight, like a.
Literally when you start a fight.
Yeah, when you load a stage, basically. It's the function that's in charge of like loading everything up to be ready. Hey, you see that? We got a DMA read.
Nice.
And now we can, every time. Yeah. Every time a game starts, we get one.
Okay, sweet.
Yeah. And if I had a breakpoint in Dolphin, which I could do, like in that, I could put one in like the DMA handler of the EXI dummy device, which I think is what you already built. And then it would do a breakpoint in Dolphin whenever that happens. Because it's calling out to Dolphin code basically.
Right. Well, it's the dummy code right now.
Yeah. But it's still that
like,
code isn't.
Like put a C++ breakpoint in.
Yeah. We can do that if you want. If you still got a little bit of time, but if you're feeling pretty done, then we can also just.
Sure. Yeah. I got a little bit of second wind. The excitement of seeing it.
Okay. Yeah. Let's do it then, because I think this is where it'll really sort of click where. Because you built your own one of these, right? EXI.
I have my own. I have my own like I think I call it frame advance.
Cool. Yeah. So you can see. This is the CEXI dummy DMA read, or whatever. So this is the DMA read handler. This is the logger that we were just looking at. So this is the code that ends up running. So if I put a C++ breakpoint here, it should break into it when we start a game.
I've never actually used a C++ breakpoint. That's funny.
Really? It's more useful if you go to debug mode. If you go to debug mode, it actually like works well. If you're in release mode, it optimizes a whole bunch of variables away and stuff, so you can't see their values.
Right. And does it put in like GDB? I've used GDB.
I haven't, no.
Like this is Windows. I don't know anything about Windows.
Yeah, I've only debugged it with like with Visual Studio. I don't know how you do it in like Linux or something else, but I'm sure it's possible. Okay, so we still have the same settings and stuff. So I think our codes should still be active because I think it's the same instance. Yeah, it's still here. And then we'll start.
Whenever I test things in Dolphin, I generally do it through Phillip actually, because Phillip always like creates a new like user directory.
Oh, really?
Yeah.
There you go.
Like,
We
oh,
broke
sweet.
we broke into the C++ code.
That's awesome. Yeah. Cool. Yeah. And I already know exactly what I want to put in that.
Nice. So yeah, I mean, obviously the point being is that if you follow this sort of structure, you can basically add a hook anywhere you want, like on any given code line, effectively.
Yeah.
So yeah.
Okay, that this has been really fun. Yeah. I'll maybe tomorrow or this weekend I'll try to get to actually implementing this.
Cool. I'll send you this exact code we built, so you can look at it.
Yeah.
And
Oh, that'll
I'll also link you to my Gecko build tool or whatever, so you can install that.
Oh yeah, yeah. Cool.
Yep. Cool.
And that calls some sort of like there's another assembler that
Yeah.
really normal.
Yeah, and I'm assuming you use Linux.
I mean I have Windows and Linux, but
Okay. Yeah, I mean, if you have questions about using that on Linux, MetaConstruct loves Linux, so
okay, yeah.
he can
I'll
help.
probably be doing it on Linux.
Yeah, because I think you'll have to install, uh, what's it called? DevKit Pro, which has like a whole bunch of like DevKit stuff. Basically,
Okay.
you'll need, I think, DevKit PPC.
Oh, dev kit. Okay,
Yeah,
yeah.
I think you'll have to install that for the Gecko build thing to work on Linux. Yeah, but that's it, I think.